Hello everybody and welcome to your video notes on quantitative energy conservation, which is about learning target 6.3 at the MEETS level. Now if you've not watched the basic level video notes yet on this learning target or understand how to use kinetic energy and potential energy equations, then you need to stop this video and go back and watch the basic level, because otherwise you're going to have a hard time with this. Alright, but if we move forward, assuming that you've watched those video notes and understand how to do kinetic energy and potential energy equations, this learning target says, I can use the kinetic energy and potential energy equations to set up a conservation of energy equation to solve for height, velocity, or work. Now let's dissect this just a little bit here. So the first idea is that we can use these two equations, which for kinetic energy is 1/2 mv squared. That equals kinetic energy. And for potential energy, or gravitational potential energy, or what I sometimes say is gravitational energy, that's mass times gravity times height. And we want to set up a conservation of energy equation. We'll talk about that. But then we want to be able to solve for height, velocity, or work. So in these equations, if we're going to there are three things that we can solve for. In the gravitational account one, we could solve for this, could solve for H, or for kinetic energy, we can solve for V. And then we can also solve for work. So we're going to do three examples, and you can see the first example off down here below where I'm writing. But before we get into that, I wanted to talk about more or less the steps that we're going to follow in all of these problems. I'm going to come over here for that. So step one, you're going to do a LOL diagram. Okay, that's going to help us get an idea of how to set up the problem. Or not only the problem, but it's also going to help us with the equation. And then step two, we're going to set up the equation. And specifically, we're going to set up the conservation I promise I can spell. There we go, conservation of energy equation. And then the third thing we're going to do, we're going to substitute in. This part will be familiar. And then the fourth thing, solve. Now, here's a little hint for you. For these two steps, the units get kind of more or less in the way and make the problem needlessly difficult. So it's going to be okay if you drop the units. Only if you need to, though. And when I say drop the units, I mean just don't include them until maybe when you set it up have the units, but then at the end have the units, and everywhere in between you don't necessarily need those. And just so you know, I will not take off points if your work does not have units on this learning target. Okay? Your answer still needs units. All right. So let's go ahead and do a problem. All right, so example one, a cart is moving at a speed of 25 meters per second. It has a mass of 40 kilograms, coasts to a stop at the top of a hill. How tall is the hill? So per usual, pause the video, write everything down for this in your notes. And then once you have that done, go ahead and hit play. And once you've got that in your notebook, you want to underline the important things and then box in what we're going to try to solve the problem for. How tall is a hill? We're going to solve for h in this problem. But in order to do that, we want to be able to set up the problem. And so what we're going to do here is we're going to start with our LOL diagram, and then from there, the equation will come very easily. So if we've got like our part A and part B, these problems are going to be a little bit more open-ended, and you're going to have to figure out some details. So figure out part A, part B, hey, that's pretty easy. And then you're going to have to define your own system. It doesn't tell us what the system is in this problem. This one's pretty straightforward. We could just say it's the cart. You could say the hill and the earth and all those other things, but really just the cart. It's moving here, so we're going to have kinetic energy. No gravitational energy or elastic energy. So we can have maybe 4 bars of energy at the beginning, and then close to the stop at the top of a hill up here. And so we're for sure going to have gravitational energy, and if it stops, no kinetic, and then there's no elastic. Now, it doesn't say anything about friction, so we're just going to assume that there's no friction. And that's okay, because it doesn't explicitly tell us we have to worry about that. So the qualitative equation that we get is EK equals EG. Now, that's nice, but we want to know exactly how much energy that's going to be. So we're going to substitute in our equations for both of these things. So we've got 1/2 times the mass times the velocity squared. That has to equal the EG, which is going to be mass times gravity times height. Okay, so now that we have those things, we can go back to our original equation and say, hey, look, this is the velocity, 25 meters per second. And then the mass is 40 kilograms. And then that's all we really need, because we have now our 1/2 times the mass, which we said is 40 kilograms, times v squared, so got our 25 meters per second squared, equals the mass, which is again 40 kilograms, times gravity, which is 9.8 meters per second squared, times h. Okay, so if you're following along with our checklist, we've now do the LOL diagram, and we just set up our equation. Well, and we've also substituted. Now we just have to solve this for h. Now immediately this problem looks a little complex with all the units and all the different things that are going on. But if you drop the units, really what we have is 1/2 times 40 times 25 squared equals 40 times 9.8 times h. And we can simplify this pretty easily. What we end up with is we just type this into our calculator and you get a number. And the number you get is 12,500. That's it. That's all this simplifies down to. And then we can also do the same thing here. 40 times 9.8. Oops. Try that again. 40 times 9.8 equals 392. And then we just have h. This problem is a lot easier to solve now. So if I want to solve this now, I just got to divide by 392 on both sides. This one goes away, and I'm left with h equals 12,500 divided by 392, and I get 31, and then there's a bunch of decimals, but if I round, I get 31.9. Now this number still needs units on it, and we know that the height has to be in meters. So I don't quite like that, but it's going to be a lot better for you than having to follow our units all the way through this time. So again, if you drop the units like what I did, you'll still get full points for this. So that's the first example. All right, so example 2 now is right here. Go ahead, pause it and write it in your notebook, and then do the LOL diagram. But really what we're looking for here is how fast. So we are going to be solving this for V. I can do this. There we go. We're solving for V this time. Gives us the mass and the height this time. So first step, we're going to do an LOL diagram. I'm just going to go ahead and show you the LOL diagram to save some time. And there we go. I said the cart was in my system. The cart starts high above the ground or above a reference point. So it has all gravitational energy. And then at the end, it's at the reference point. So we'd say it has only as kinetic energy. And then now it's time to set up our equation. So we've got EG equals EK, pretty similar to the last one. Mass times gravity times height is EG equals EK, which 1/2 times mass times velocity squared. And then we just substitute in the values that were given to us up here. So the mass is 150 kilograms and the height is 30 meters. Okay, so now I've got my mass, which is 150 kilograms times gravity, which on Earth is 9.8 meters per second squared. Promise that's a squared. Times the height, which the problem said was 30 meters. So we've taken care of the left-hand side. That equals 1/2 times the mass, which is 150 kilograms, times velocity squared. Now the velocity is what we're going to solve for this time. So this is what we need. I've got all these other things that we just substituted in. And now I just need to solve for V squared. But again, I'm going to drop the units. And so now I have 150 times 9.8 times 30 equals 1/2 times 150 times V squared. That looks a lot easier to solve now compared to what it was before. So what I'm going to do now is I'm going to calculate these in my calculator, and then I'll write the answers right here. So the left-hand side equals 44,100, and this side equals 75 times V squared. And we divide both sides by 75. And that goes away. And I'm left with V squared equals 4,400, or you know what I'm trying to say, divided by 75. Take the square root of both sides, and we're left with V equals 596, and since it's velocity, it has to be meters per second. And there you have it. And here's example 3. This one's going to be solving for work this time. Now go ahead and copy down everything you have on the screen. I'm going to do the LOL diagram. All right, here we go. So at the beginning, we have the box that's on the spring and then ends up in the air, and it's still moving, as we can see by the swooshies. So the hint at the end is do not include the spring in your system, and we want to figure out how much energy was stored in the spring. So if we set the system to just be the box, we end up having to have energy enter the system from work and then ends up as kinetic and gravitational in the end. So to set up our equation for this, we end up with the work equals EK plus EG, and that the work equals then 1/2 mv squared plus m times g times h. Okay, go ahead and see if you can solve this now. I'm going to just substitute in and solve. And here you have, I haven't solved it completely yet, but you can see that I substituted in the mass, velocity, mass, gravity, and height, but then the units got annoying, so then I just dropped off the units, and now all I have to do is type this in my calculator, and then I'll find out what the work is. And I end up with 6,770 joules.